I think we're going to go ahead and get started for the last lecture of reinforcement learning. Before I jump into the topics, does anybody have any questions from yesterday? All right, so today I'm going to do lecture a little bit differently. I know 5 hours is a short period of time, but I wanted to make sure to talk about some of the exciting frontiers in reinforcement learning. We started talking about that yesterday with some of the sample complexity results. And in general, there's a huge amount more to be done in that space. Another space that I'm personally particularly excited about is counterfactual reasoning and batch reinforcement learning. And I got really interested in this about 5 years ago. I was collaborating with Zoran Popovic and 2 graduate students, Travis Spandel and Ringen Liu, and we were curious about the following problem. So this is the game Refraction. In it, kids learn about fractions by splitting laser beams to feed spaceships. So what they do is they have these little splitters, and they can use it to split a ray of energy to try to feed a spaceship like the one that you see up there. And they have different sort of splitter options, and the different sort of activities include different types of fractions like a third or a half, and different types of knowledge concepts we want to teach people. And the question that we were trying to think about in this case is, what, given the history of previous activities we've given to the student and their performance on those activities, what is the next activity we should give to them? And so that's how it relates to reinforcement learning. So we would think of something like this. Maybe, depending on whether they took less than 30 seconds to complete the previous level or more than 30 seconds to complete the previous level, we would give them different activities next. Now, that's obviously a very simple state representation, just amount of time. And you could imagine all sorts of much more complicated, what did they actually do? Did they make mistakes, et cetera? And using that information to try to figure out, what's the next activity to give to them. And in this case, we were particularly interested in persistence. This is an optional game. It's been played by several 100,000 students. But it's on the web. People can drop out whenever they want and go look at Facebook instead or any other activity. And so we were trying to figure out how do we get people to persist, particularly if some of the stuff might be hard or challenging for them. So our objective or our reward function here is persistence. And what we wanted to figure out is how to do reinforcement learning. Now, the challenge or the setting that we had here is that most of the time we didn't want to do things that were really ineffective for student persistence and learning. And so we wanted to use the existing data that we had to try to improve, get a better policy for future deployment. So the setting was that we had about 11,000 learners' trajectories where we had taken random levels. So we'd given, a student, we'd selected from all the different levels or activities we had in random orders for those students, and we look at how long they persist. And the question we were trying to answer was, what would be a good new policy, given that old data, to maximize student persistence? So this is a batch or offline learning problem because we're not going to allow our algorithm to actually collect new data online. It just is reliant on those previous state, action, reward, next state pairs or tuples. And we want to use that to figure out how to act in the future in a way that we think is good. So if we think about how this relates to the general framework of reinforcement learning and what we've been thinking about, just as a recap, reinforcement learning, we have our value function is equal to our immediate reward plus our expected discounted sum of future rewards, where I've assumed the Markov structure here. And the setting that we're going to talk about today is sort of counterfactual or batch reinforcement learning, where the setting is that we're not dealing with the exploration problem. We're given a set of data. And generally, we're going to think of those as a set of trajectories. So this is the episodic reinforcement learning case. So we have a set of n trajectories. And then they were generated by a particular behavior policy pi. So this is a behavior policy. And generally, we're going to assume that to be known, but it is not always known. So in the context of this refraction game, we knew what it was. It was random. It was the pi of a given s was just equal to 1 over a for all a. It was just random. But it could be unknown. So when we look at some of our healthcare applications, that involves looking at healthcare records. And if it's a randomized controlled trial, you know what the behavior policy is. But if it's physicians, you don't. Like, you don't know. They don't give you a, this is the probability I prescribe aspirin versus Tylenol. So you can try to infer it from the data, but you may not know this precisely. So this is the setting that we're interested in. And I think it involves a number of important challenges that are common to reinforcement learning. And I think, but reinforcement learning setting has a couple different additional situations. So part of it is it involves this what-if reasoning, given that, let's think about, a sequence of patient treatments and looking at different outcomes. And then the question is what we should do for a new patient. And one of the big challenges there is that, like in bandits, like in reinforcement learning, we have censoring. So I can't see what would have happened to the same patient if I was to do a different sequence of actions. So that makes it challenging. And then in addition, we need generalization. And I think this is particularly important in reinforcement learning because we have this sequence of activities we're taking. So we essentially have A decisions here and A decisions here. And in general, you could think of there being an A to the H space, where H is the number of decisions you're going to make in an episode. So that's enormous. Historically, randomized control trials have focused on a single decision. There's certainly ones now that are starting to think about sequences of decisions, but a space of A to the H is going to be way too impossible for us to possibly have a different randomized control trial bucket for each of those. So we're going to need some ways to extrapolate and say, well, maybe if I did, condition A and then condition B, or condition B then condition A, can I extrapolate from that and understand what it would be like if you did condition A, condition A? So can we sort of interpolate and extrapolate from the data that we have in order to reason about the full space of policies? So I think in general, this is a really huge area. Historically, there's been a huge amount of interest in causal inference and understanding, what actions have impact on the world. And there's this a very big area in things like epidemiology and biostatistics, et cetera. In fact, does anybody here work on this topic? I'm curious if anybody's already done work. So nobody here, but this is a very important area in econometrics and a number of different areas where we'd like to figure out what's the right thing to do. We'd like to be evidence-based and use our data to try to inform better decision-making. And recently, there's starting to be more intersections between the machine learning community and these causal inference communities. And the question from a mathematical perspective is we have some sort of batch optimization problem. So what we would like to do here is we'd like to think about what is the value of a policy. And this is going to be an estimator, statistical estimator. So we're going to take in a set of data. This is our data set D. And we would like to say, on average, what is the performance of this policy? And we want to pick a policy, again, a mapping from states to actions. And you might have different policy classes. So you could imagine maybe you have a linear threshold policy, which says if they take longer than 30 seconds on this level, then I do X, else I do Y. So you could have something very simple. Or you could have a deep neural network that conditions on all of the history and exactly where they've placed things, et cetera. So you could have very different function classes and hypothesis spaces. And so you might want to be doing some form of model selection. You can think of this as model selection. And we just want to figure out whichever one of these is best in a way that gives us guarantees for the future. So we don't really care about how well we're doing on our training set. What we care about is that the policy that we pick when we deploy it is going to do well. And we can think about separating these two into two distinct questions. One is policy evaluation, which we started to talk about before. Q-learning was one way to do this. Q-learning allowed us to estimate the value of the optimal policy while acting in a different way, subject to some conditions on our action selection. In particular, we assumed there we could take all actions in all states infinitely often, and then we were guaranteed to converge. But we've talked about some things to do this, so Q-learning could be a mechanism. And we also briefly talked about function approximation and ways to do this, so something like fitted Q-iteration, which we discussed very briefly. And then policy optimization probably reminds you of policy improvement. So like when we did the policy improvement algorithms, and we sort of had a policy evaluation step and then policy improvement, here we'd like to be able to compare over a large set of policies. And so we can decompose this problem into those two. But a critical question here is, how good are these? And we want to be able to have guarantees about their performance in the future if we're going to deploy them in high stakes environments, like for kids in healthcare or for education, et cetera, or consumer marketing. Okay, so I just want to highlight here, this may start to look somewhat similar to things like structural risk minimization. And I want to highlight that there's a number of important choices here, even compared to that setting. So first question is, what is the hypothesis class that I'm talking about here? Is it a set of models, like a Markov decision process models? So what would be a difference in different types of Markov decision process models? So these here is defining a transition model and a reward model. And you could imagine thinking about different forms of state spaces. So maybe you have a state space which is just equal to greater than 30 seconds, less than equal to 30 seconds. Or maybe you have a state space which is equal to all prior history and moves the student did. So these are defining different Markov decision processes. A second thing you could have is have hypothesis spaces over your value function. You could assume that your value function is linear regression on some features. You could assume that it is a deep neural network, etc. Or you could do this directly over your policy class and pick different policy classes. So compared to a lot of settings and with supervised learning, where it's more clear exactly what even our hypothesis space definition is, here we have sort of three main different objects that we could define hypothesis spaces over and then do maximization over those spaces. Now, I think, well, I'll just highlight again that this is not going to be a comprehensive overview. This is going to be my perspective on this particular problem. And I think what I'll start with here is policy evaluation. And remember, when we're doing policy evaluation here, the goal is that we're going to be trying to find a very accurate estimate of a policy, with the intuition being that if we can do accurate estimates of the policy, so if we can get highly accurate estimates of the true value of pi. And what do I mean by the true value of pi? I mean if we really deploy it in the environment. So if we really deploy this and we get v pi, so if this estimate is close to v pi, then that should be helpful for policy optimization. Because if all of our estimates of the policies were perfect, we had no error, then we could just take a max over all of those and we would be guaranteed to do the right thing. So there's been a lot of focus on policy evaluation in the reinforcement learning communities, in part because it's considered, if we could achieve this, then that would help us for optimization. It also often could just be important within its own right. So for example, a company might be interested in, okay, we're thinking about deploying this new particular policy. How much better is it than the current policy? And so sometimes you're interested in this in your own right, even if you're not doing policy optimization, but it's also considered sort of a sufficient condition. If you do this really well, then you can do optimization on top. Now, historically, there's been a huge amount of work on this problem, again, from econometrics, epidemiology, et cetera, but most of it is focused on one decision and it being binary. So we're thinking about things like treatment effect estimation. We want to understand whether or not the choice of now prescribing a drug compared to some control, maybe an injection, if it is significantly better. And often for whom is it significantly better? So a big question often here is in heterogeneous treatment effects. Which we can think of as being like a contextual bandit in a way, because we're just trying to understand for what is the best arm to pull for each different context. So there's been a lot of work on this in this case, but we have an additional challenge when we start to move to the reinforcement learning setting. And I think that's really nicely illustrated by this figure that was in a Nature Medicine paper by some of my colleagues. So this is looking at what would happen if we try to use medical records to try to figure out from those medical records what's a better policy to deploy in the future. And what it's illustrating is the challenge of doing multiple decisions. So let's imagine that we start off with some cohort. So we have a whole set of patients that we're interested in figuring out if we can derive a better treatment plan for these people. So this is the start. This is time here. Time is on the x-axis. And we say, well, in our policy, what we would do first is we do mechanical ventilation. So this is what our policy says. So that means that we have to ignore all the people that didn't get mechanical ventilation at that time point, and so that's represented up here. So these just drop off from the point of view of our algorithm of people that we can use to evaluate how good our desired policy is. So then we end up here, and then we say, well, if we, under our policy, if they experience discomfort, then we're going to use some amount of sedation. And so then again, in the real data set, some people didn't get sedation, and so then you lose that cohort. And essentially, in this case, what we can see is that not only do you get the normal censoring issues that you would get with multi-armed bandits, but the problem here is that different policies, by definition, will take different actions in some states. And if we assume that we have a dynamics model, that will likely incur different distributions of future states. That's normally part of the goal. And so that means that we end up with different state distributions under different policies. But we really care about people that look like what we would see if we were to deploy our new policy. So after we take these series of decisions, you may end up with a very small number of people that match the policy you're trying to evaluate. And in general, this drop-off can be as bad as exponential. Because, let's say you're just randomly assigning people to different conditions. There's 2 conditions, you're randomly assigning them. Then the probability that you're going to match all the way through after a time period is going to be 1/2 to the h. Yeah?
This assumes that the data collection procedure was completely randomized.
Great question. Okay, no, maybe. It depends. So the different methods I'm going to talk about involve different, in order to have any guarantees that these are consistent estimators, they're going to need to make different assumptions. Often they require ignorability and lack of confounding. And the lack of confounding is going to mean that it doesn't have to be random. It doesn't have to be a randomized control trial. But we do have to assume that all of the features that were being used, say, by a physician to make a decision. So if this is a physician's probability of taking an action given a state, let's say this is really, the physician. This is our behavior policy. In order for our estimates to be accurate, we have to assume that we have access to all the covariates or all the state features which were used to make that decision. So if I'm a doctor and I'm deciding how to treat you now, from the perspective of my algorithm, I don't have to know exactly what that probability distribution is, but my algorithm has to have access to all the same information that the physician did, because otherwise you could have the following. And this is a really important issue that we don't really know how to solve very well yet to tackle observational data. Otherwise, let's say the doctor notices, for example, that someone has one blue eye and one green eye. And for some reason that tells them something about, the particular medication that's appropriate. But that information isn't recorded in your electronic medical record system. So later when your algorithm is trying to make a decision, it says, oh, I should always give this treatment, maybe just based on whether they're tall or not. But actually there's this critical feature. And so if you don't have that information, it can basically change the coverage of whether you can accurately estimate the value of your policy. And so a critical assumption here normally is that we have no confounding. We have all the same access to the information that the behavior policy did. And that's a big open question about how well to deal with that. People think about this a lot, sometimes in a less statistical sense, more graphical model sense. We're starting to think about it in terms of bounds on the treatment effect. How much can confounding change your treatment effect? And I think it's a really important question because if we could solve it, then we could do much better with observational healthcare records because most data is observational. It's not a randomized control trial. So great question. Anybody have any other questions about this setting? Okay, so this is a big challenge, and this is a different challenge than what we see in if you're making a single time step, because you don't have this like whittling away of your cohort that can be sort of as bad as exponential. So that's going to be a big problem in terms of variance. So I'm going to briefly go through the classic ways to do policy evaluation, and some of these are going to look very familiar or very similar to the methods we were talking about before. The first is model-based. So in the model-based approach, we can estimate our dynamics and reward model from data. We talked about that a little bit yesterday with the NBIEB algorithm, where we took our data, we just averaged it to get the average reward, or we averaged it to get the average dynamics model. So this is, in NBIEB, we did this. Now, in NBIEB, we did this, and then we tried to compute the optimal value function plus some bonus. In this case, we're just doing policy evaluation. So once we have those models, we can just use them to evaluate the policy, including analytically. So this is the analytic expression. Again, that can scale roughly, s to the 2.3 to 3, because we're doing an inverse here. So it may not be computationally tractable to always do it analytically, and you could do it another way. But essentially, we're just going to do policy evaluation, and you could use any of the policy evaluation techniques we talked about before, like temporal difference learning or Monte Carlo, et cetera, using our fake model. Now, I'll just first say, the problem with this is, as you might expect, that these models are approximate, and just like how NBIEB had to add in this bonus term because your models might be wrong, similarly here, we're not adding in bonus terms right now, so this could be biased, and it could be asymptotically biased. So this is biased, and may not be consistent. Depends on the parametric form you're using for this and for this. And as a simple example of this, if we think back to the refraction case, you can imagine us using a really simple model of students, which is that their state never changes. It doesn't matter how much we give them different activities in refraction, their knowledge never changes. It's not a very good state representation, but certainly one you could use. And in that case, we could estimate the parameters for that state representation, et cetera, but no matter how much data we get, we would not get an accurate estimate of the value of a particular policy. So generally, the problem with models, like what we talked about a little bit before with TD versus Monte Carlo, is that they're going to have less variance, but they can be highly biased. A second approach is model-free function approximation. And again, we talked about this before. We talked about TD learning, and that was for the tabular case. And then we talked very briefly about fitted Q iteration, where we talked about parameterizing our Q function, our value function, with a parameter theta. So this is a parameter vector. And this can either be something like linear regression or deep neural networks, et cetera. And then in this case, we have a particular policy that we're using for the backup. So we're not taking a max. We're just using the action that we would take under our policy. And then we try to fit a function that minimizes this. This can have some known problems in terms of convergence results, but under some quite overly strong assumptions, in my opinion, but nevertheless, I think it's still really nice progress. There's some nice results showing that under some conditions, these things can converge. You have to have some conditions under sort of the distributions of states and actions and the accuracy of your function approximator to be able to estimate your in-between value functions as you get towards sort of converging for your Q function. There's some very nice recent work on this. ICML had several papers. Let me see if I'll plug that out and plug this in again for a sec, because I think the pen died. I'll write it on the board while we're doing that. At ICML this year, had several papers, one from Nan Zhang's group, and one from Yisong Yu at Caltech. Both looking at essentially batch function approximation with fitted Q iteration and providing formal theoretical bounds on those cases. One of the reasons why I think that this is also important is because of the connections to deep learning, connection to deep brain connections too deep RL. Because these type of model-free value function approximators are used so extensively right now, if we can understand their theoretical properties better, then it gives us a potential platform for further informing the types of algorithms we want to design and run. All right, let's see if that works. So the next thing that one could do, well, okay, so those are two ways we could do this. We could do model-free or we could do model-based. And those provide us with parametric models, either of the dynamics and rewards or the values function. And as I was mentioning, the benefit of these is that they're generally lower variance. And the downside is they're biased, and they might be asymptotically biased. And so they're generally not going to be realizable unless we make a strong assumption that our true value function lies within the parametric form we're using, or we're using a sort of a non-parametric approximation. So an alternative is importance sampling. And just, I think Kevin covered this, but can you raise your hand if you remember the importance sampling lectures? Okay, so a few people remember it, but I wasn't at Kevin's lecture, so I'll go through it briefly, at least as it applies to reinforcement learning. So an alternative to, where are we going? We're saying, well, parametric models are low variance and potentially high bias. So you might think, well, maybe there's something that's unbiased that potentially has high variance. And that's importance sampling. So importance sampling is this beautiful trick of saying that if we want to figure out the expectation of a random variable with respect to a distribution P, so we'd like it with respect to P. This is what we want. That we may not be able to directly sample from P, or we may not want to directly sample from P, because it might be that there's some really, really low probability events, and so it's not a good idea, but those dominate sort of our expected value, or we just can't directly sample from P. So this, in our case, this is going to be what if we were to use a different policy than the one that we use to run. So the beautiful insight here is to say, well, we can just multiply and divide by the same thing. Q is just a different probability distribution. So we multiply and divide by that. So we're multiplying and dividing by 1. And then we can say, well, this is approximately equal to if I sampled points from this other distribution Q, and then I reweight them. So this is the importance sampling weights. So it's very simple and elegant, and it says if you want to get the expected value of a random variable under a distribution P, what you can do is you can approximate it by a set of samples. We can always do that. We can always approximate things by a set of samples, but the cool thing here is we can approximate them by a set of samples that were gathered under a different distribution, and then we just reweigh them. And we say for each of those, we look at the ratio of what we would have, the likelihood of selecting that point under our desired probability distribution function compared to the one we sampled under. Now in this case, we have to know both right now. So we're assuming that we know what P of X is and we know what Q of X is. And so let's see now how that's going to translate to the reinforcement learning case. So in the reinforcement learning case, we're going to want to do the same thing. We're going to assume that we care about figuring out the value of a policy. And the way one way to write this down is we can think about T here as trajectories. So tau is a trajectory. Or, you can think of it as a trajectory or an episode. So this is a case where we have S, A, R, S prime, dot, 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 dot. And one way to think about what the value of a policy is just to say, what is the probability of that policy generating a particular trajectory times the reward of that trajectory? So this here is the sum over T equals 1 to the length of horizon of all the rewards in that trajectory tau. Okay. So this just says, the value of my policy is equal to the probability I get a particular rollout or episode times the sum of rewards in that episode, and then I average. And so what we're going with here is what I want to show you is that we're going to be able to use a different policy to generate the data, and then we're still going to be able to play this importance sampling trick. So one thing that we could do in this case is we could do sum over tau probability of tau given pi s divided by probability. So here, tau is generated according to pi to start. And now I'm going to have tau given pi, a different behavior policy. So we can think of this as the initial state. Times r of tau. Times probability of tau given pi b s. So I've multiplied it and divided by the same thing. And I've just said, well, what would have been the probability of generating this trajectory under an alternative policy? And then what I'm going to do is I'm going to change my sum here to say, well, this is going to be approximately equal to 1 over n sum over tau generated from my behavior policy times the probability of that trajectory under my desired policy divided by my probability of trajectory under my behavior policy times r of tau, where I push this part to here. Okay. So the next question should be, well, how do we actually evaluate what is the probability of a trajectory under the policy? And remember that we don't know the dynamics model right now, so that should be slightly concerning. But the great thing is that that it turns out the dynamics models cancel. So this is going to be equal to 1 over n sum over tau sampled from pi b. And then we can think of this as just being a product of t equals 1 to h of the probability of s prime given, or s t plus 1 given s t a t times the probability of taking that particular action under my policy for that state. So that's how we can write out the probability of a trajectory as a combination of probability we take an action times the probability of that transition. Now, many of you might be thinking, but wait, most of the time we've been thinking about deterministic policies, so isn't the second probability just, isn't this term just either 0 or 1? If we are going to be, it certainly can be, particularly for the policy we want to evaluate, but for our evaluation policy, it's almost always going to need to be non-deterministic so that we can evaluate alternative policies. If in your data you only always take the same action in one state, you can never evaluate what it would be like to take a different action from that state. So like if I always treat patients with Tylenol, I just can't know what it's like to treat them with aspirin. You have to have stochasticity in your behavioral data. So it looks like this on top, and then it's going to look almost identical on bottom, which is great because then we're going to get to cancel things. Times the probability of AT given the behavior policy, all times R of tau. Yeah? Sum over A.
What is A?
The action that was taken in the trajectory.
So we're looking at the probability of picking a particular A, right?
Yep.
So do all the possible A's?
No, this is so this is, AT is the actual, thanks for the question, AT is the actual action that was taken in that trajectory. So I didn't, for space, include, let me see if I can index it. So if we write it down here, we'll assume that the taus are sampled from pi b. We're going to sum over I equals 1 to n, so we're going to have n trajectories. And then I will index each of these by I. So these are the actual states that were visited and the actual actions that were taken in that trajectory. So I have a particular trajectory of state, action, reward, next states, etc. And that is going to be completely defined for one trajectory. That's like how we actually treated the patient. And then we're going to say, under our behavior policy, how likely was it that we took that action versus under our desired policy, how likely is it that we have this action? Yeah. And so the nice thing is that these things are identical, so they cancel. So this is then going to be equal to 1 over n sum over I equals 1 to n, product over pi of AIT given pi SI divided by probability of AIT given pi B SI for t equals 1 to h minus 1, and then all times the sum of rewards for that particular trajectory. So this is great because what this says is that I can use data from another policy and I can reweigh it so that I overweigh things that look like the policy that I care about and underweight things that don't look like the policy I care about. And I don't have to know the dynamics model, which is great because I don't know the dynamics model because it cancels. And so, and this is just the actual reward I've observed. So it says that all I need to know in this case is the probability, and these are policies that I'm going to assume I have access to. So I have access to the behavior policy. I certainly have access to the policy I care about. Yeah?
How does this interact with confounding like you mentioned earlier? Like if the behavior policy is like marginalized over the variable?
Yes. Huge problem generally. So the big problem can be, the big issue for, let me write down some of the conditions, what we need for this. What we require in this case is that the probability of A given pi, the policy that we care about, if this is greater than 0, then P of A given pi B and S has to be greater than 0 for this to be valid. So what it says is that if there's some chance I would take a particular action, some chance that my policy would prescribe Tylenol, then in my behavior policy there has to be some chance that I would also prescribe Tylenol. It has to be non-zero. If I would sometimes prescribe Tylenol and my behavior policy would never prescribe that, then I'm not going to get a good estimator. And that's essentially, and we often call that coverage. And the problem really with confounding is coming in with coverage because you're getting partial aliasing. So if you think you have all the states that you don't, and you don't, then it may appear that this probability is greater than 0, whereas for some cases it's not. Like, so it might be for some really sick patients, I never intubate. But because I'm missing that variable, it looks like I do, so my policy thinks, oh yeah, I can fairly evaluate what it would be like to intubate these patients. But in fact, that's where we have 0 coverage, and so we get a biased estimator. Great, oh yeah.
Do you also require an upper bound for that fraction?
Do I require an upper bound for that fraction? Good question. We will generally, depends on the bounds we use. So often the bounds in terms of concentration inequalities will generally depend on an upper bound for this. The upper bound for this can be awful without further assumptions. So this generally can increase exponentially with h. In practice, for a lot of the proofs, we often assume these that there's some bound on the ratio. Now, I'll just highlight there that not all is lost in the sense that if all of your rewards are positive, if you end up doing, often people call this as clipping the importance sampling ratios. So you can just arbitrarily bound this to make sure these don't go insanely high, and then you just sort of clip or drop and don't let it grow beyond a certain amount. And what that will do is it'll make your estimator biased, but it'll make it biased in a particular way, which is downwards. And if what you care about is, I want a lower bound on how good my new policy is, which you might, because you might say, I'm only going to deploy it if it's really good. And so if my lower bound says it's really good, I'll deploy it. Then that's kind of a conservative estimate. So sometimes people will just clip these to prevent the variance getting too large. Questions? Okay, so this is what this looks like in the same as what I just did. So we get this nice ratio, which is independent of the true dynamics. And the really cool thing here too is that this does not make the Markov assumption. So no Markov assumption needed. Because while, particularly for space, I'm only writing here that our dynamics model is like a Markov model. Your dynamics model doesn't have to be a Markov model. It could depend on the full history and it would still cancel in the numerator and denominator. So the nice thing about this estimator is it's making no assumptions that the world is Markov, and you can get this cool structure. Okay, so this was first introduced, I don't recall exactly when the statisticians came up with importance sampling, but from the reinforcement learning perspective, it was around 2000 where people started talking about this, particularly for off-policy evaluation. And then there's been a lot of follow-up interest by our group in particular, but also a lot of great work by Scott Neekham and Peter Stone and a number of others. So people have been thinking about this a lot, particularly with this challenge with the high variance, but unbiased. So this is a consistent estimator. Asymptotically, it will always converge to the right thing. But in general, as we proved, and I'm sure other people have too, the variance can be exponential in the horizon, which is bad, particularly for long decision-making cases. All right, I want to highlight that there's one of the recent nice innovations is thinking about how do we get rid of this really high variance. So I think that this issue has prevented sort of off-policy evaluation using importance sampling perhaps to be used as much as we might hope. And there's been a few different groups that have been thinking recently about a different way to pose importance sampling in the context of sequential decision-making by leveraging some of the Markov structure. So recall that in the Markov decision process case, if you fix the policy, then that induces a Markov chain because you know what the action is at each time point, and so you end up with a Markov chain, and if you run that policy for long enough, it'll be a stationary Markov chain. It will have mixed. And so that's the insight that has come up within sort of the stationary importance sampling, SIS, for RL policy evaluation, that several different groups have kind of independently been thinking about very recently over the last year or two. And here's the insight. The insight is that what I wrote down before, so what we had before was that it was equal to the probability of a trajectory times the reward of a trajectory. That's what I had before. But an alternative way to think about this is that it is a weighted sum over the stationary distribution over states and actions for the Markov chain induced by pi. So as this chain mixes, eventually we'll have sort of a stationary distribution over states and actions times the reward for that state and action. So this is an equivalent way to think about what the value function is. Now this is making a Markov assumption. So this is assuming Markovianus. But the nice observation is that once we think about it in this way, we can play the same importance sampling trick, but instead of doing it over trajectories, we can do it over state action distributions. So this is just equal to sum over SA, d pi of SA, divided by d pi b of SA, the stationary distribution under your alternate policy, which means this is approximately equal to 1 over n samples where, we've got SA pairs sampled from pi b, and then we reweigh them. Oops. In the same way we did for importance sampling. So the nice thing there is now we've gotten rid of this product. Before we had this product from 1 to h. Now we don't. We just had this stationary distribution. And so in principle, this might be much lower variance. And in practice, we observed this as well. So all three of these papers thought about deriving this from the policy evaluation perspective. The Galetta-Bellemare paper also thought about using this for control decisions. We have a recent UAI paper, UAI 2019, which is using this to do batch policy gradient. One thing I find, for those of you that are familiar with policy gradient, we didn't really talk about it here, I find really unsatisfying about it is that you always throw away all your old data, and you just use data from your current round, which seems super inefficient. And what this gives us is a nice way to better use all of our previous data without having the variance explode. Yeah?
The stationary distribution is only a limit of further distribution.
Right.
So this is a new definition for the policy evaluation, not the previous definition?
Good question. So the question was saying that d pi of SA is the sort of asymptotic after things have mixed. And so is this a different definition? Yeah, in this case, we have to be a little bit careful about whether or not we're assuming we're in like the infinite horizon case. In practice, this is tricky because your episodes are finite for any real data set. So you can either ignore this, or you can try to do it for the per time step, or you can include discounting. So you're absolutely right. There's a couple different additional things you have to be a bit careful about. And in general, estimating the stationary distribution is non-trivial. And at the beginning, you certainly don't expect your process to be mixed. So now we have these two different types of things. We have parametric models, dynamics, rewards, and or value functions, which are going to be low variance, potentially high biased. Now we have these other things, the importance sampling techniques, which are unbiased under certain assumptions, and they can generally be very high biased, have very high bias. And so a natural approach is to do doubly robust estimation, so we're going to just combine these. And this is, again, an idea from statistics. And this was first brought over, to my knowledge, for bandits. Kevin might know in earlier examples, but the first example I know of for bandits was by Miro Dudek and some of the Microsoft research colleagues. And the insight here is to say, well, can we combine between these two estimators? And there's a couple motivations for doing this. We might want to combine between these two estimators to try to get to lower variance. And another thing we might want to do is, let me just bring it back here. So when we were talking about this, so far we've been assuming we have access to the behavior policy. If you don't have access to it, but it's not confounded, you can estimate it from data. If you estimate it from data, it's going to be wrong with finite amounts of data. And if it's wrong, then you have something that's wrong in a denominator, which can cause havoc with your estimator. So in general, errors in the denominator can propagate, particularly in the reinforcement learning case, really badly, like exponentially. And so one of the other motivations for doubly robust estimators is to say, if we are instead estimating our behavior policy, instead of being given it, then we would like to be able to either sort of leverage our parametric model for the rewards if they're pretty good, or be more robust to sort of error in the importance sampling weights. So this can both help with variance and model misspecification. For the reward model or pi b. And what it does is it basically says we're going to take, so the value function estimate, I'll write out all of these. We're going to assume that we have some parametric models and do some amount of importance sampling. What we have here is we have v hat is denoted to estimate our model, and that's going to assume that our policy is stochastic, so we do a weighted average of the probability of taking action given a state times our model of the reward. So this could be a deep neural network, this could be linear regression. And then we have our rho here, which is our importance sampling weight. And so we're combining between these two estimators. And again, this is an idea from statistics that was brought over to the bandit literature, particularly in the context of thinking about this for web article recommendation. There's a few papers from sort of 2010, 2011, people like Li-Hong Li, John Langford, Miro Dudek, and a number of others published several papers while, at least several of them were at Yahoo, showing how this could be used to optimize for web placement of news article recommendations. Yeah?
Is the second term served as a control variance?
Yes, exactly. So you can think of this as a control variant. Also, for those of you familiar with policy gradient, you can think of this as being a baseline. Okay. So then it was brought over to the reinforcement learning community relatively recently, in 2016 by Li-Hong Li and Nan Zhang. And the idea now is we're again going to sort of have a covariate term. So we're going to think about an estimate of the model. So this is going to be our parametric Q function that we fit in some way. This is our parametric value function. Here I've used slightly different notation. I'm using pi e instead of pi, so this was equal to pi before. And then this is just showing which trajectory we're in, hi. And these are the real rewards. And these are the weights. Importance weights. And so this is what that looks like in this case. And just like in the doubly robust estimator introduced by Muro, this is unbiased under some conditions over, under some assumptions, under some conditions on, in this case, I believe they assume that you know the importance sampling weights. So you know the importance sampling weights. And so it's unbiased in this case if you do this particular formulation of the control variance. When we were thinking about this, we were thinking of that as a limitation. So asymptotically, I think it's really nice if your estimators are consistent. But when you're dealing with finite amounts of data, you may not care if the estimator is unbiased. You may want just a really good estimator. You may want highly accurate or sort of low mean squared error. And so with one of my previous postdocs, Phil Thomas, who's now faculty at UMass Amherst, we thought about just trying to directly optimize for accuracy. Accuracy being mean squared error and being a combination of our bias and variance. And the idea that we were thinking of is a fairly simple one and same motivation for what doubly robust is doing, which is we have a model-based estimator with high bias and low variance, and then we have importance sampling estimators with low bias and high variance, and couldn't we just kind of directly optimize to figure out how to trade these? Now, let me just highlight that this is not a trivial problem in the sense that bias is equal to the difference between the true value of v pi and my estimated value. So that's equal to bias. So if I actually knew what bias was, I'd be done because I would have my estimator and I'd have my bias and then I could just correct for it and get the right value. So it's not like we can directly observe this. So if we're going to want to try to get an estimator that does the best of weighing between bias and variance, we're going to need some way to approximate that or to bound it. So we introduced a couple of different, this is an ICML 2016 paper, a couple of different estimators. One is building on the observation that just like for weighted importance sampling, which I'm not sure if you guys talked about before, but is a common trick to greatly reduce the variance for importance sampling, and we'll have a question on that later today, that we can do that for the doubly robust estimator too, and that can make a very big difference. So much lower variance, small bias. And empirically, it often does extremely well. So just a really simple reweighting. I will note here, so the estimators that we're talking about, and generally a thing to consider for the policy evaluation case is how important is it to be asymptotically consistent? So there's, again, a nice paper from ICML this year looking at a couple different interesting examples where they're doing a comparison of several different policy evaluation methods. And what they were finding in this case is that, so this is the true value. This is essentially amount of data. You can think of this as having more data. And this is fitted Q iteration, which in general is not guaranteed, except for under strong assumptions. You can see here that empirically it's doing very well, and it's doing better than weighted doubly robust, which was this method we proposed a couple years ago. So you can play a price for the fact that you want to be asymptotically consistent. Now, when I talk to my statistician colleagues, they say, well, there's no way we could do fitted Q iteration because it's not consistent, and like we have to have that property. And then I think in some scenarios that's very important, and then in other practical scenarios, it's fine, and you know, given the amount of data that you have, maybe you just care about practical performance. So I'll skip through this very briefly because I want to get briefly to additional ideas. We had some other ideas for how to further improve the accuracy. It can make a big difference to data efficiency. So I like to highlight here that the implications of being able to do these things better is that you could need vastly less data to answer questions. So this is a tiny example. This is just illustrative, but the idea here is this is the amount of data you have. Our estimator here is needing basically 1/10 of the data, which means that also if you have a problem where you just don't have very much data, you might be able to figure out a policy that's actually better than what you have right now because you have so much better estimators. Okay, so I'm going to now switch very briefly to just highlighting the issues with policy optimization. So we just said we could do policy evaluation. How would we actually pick a policy? This is, let me just skip to kind of one of the main ideas there, which is, turns out it's quite subtle. If you're just picking models, then they're biased, and it might be hard to select policies. Even if you're doing importance sampling, it may be, it can be unfair. And what I mean by unfair there is that you can systematically pick the wrong policy. And the intuition for this is that your importance sampling estimators can have very high variance. And so if you have two things with very different variances, then when you're taking a max over those, then you can start to get bias. So this problem is non-trivial, just solving policy evaluation. If we can't do it perfectly, it's going to be challenging of how do we use that for policy optimization. And so what I've been very excited about over the last 3 to 4 years is thinking about how do we solve and work towards something that looks like this. So I think most of you are familiar with structural risk minimization, and I think we just don't have that for reinforcement learning. So when I talk to my colleagues, or particularly people that are not colleagues, about using reinforcement learning for their problems, they say, well, I know about machine learning, you have a training set, you have a test set, so can I just give that and then we'll know the policy works and then we can deploy it. And we just don't have that yet for reinforcement learning. I would like to have something like formal bounds on that once I pick a policy, what is its performance going to be in the future? And it might look something like, depending on sort of the VC dimension or some other characterization of the complexity of the hypothesis class for the policies I'm considering. And I think that would be great. And then I think also then we could have something like cross-validation as an empirical tool that people could actually use. I don't think we're close to this yet. I think there's some nice progress for the bandit setting. We have some progress in some other aspects, but there's a lot to do. So this then means that we need not just policy optimization and policy evaluation, but we need some error bound. Let me just highlight sort of some of the steps towards that. So I think that the error bound part is the really hard part. Importance sampling bounds, you can use and get bounds on top of these. So you could do things like Hofting inequality and other aspects. They tend to be enormous, like what was asked before. Do you need a bound on that product of importance sampling weights? That typically appears in your Hofting bound, and so it's enormous. So often you end up with bounds that are just vacuous. So that can be challenging unless you have an enormous amount of data. A second approach is to use particular function approximators, but they typically need a number of samples that's exponential in your input state dimension, so that's going to be hard in terms of scaling. A really popular approach has been to think about fitted Q iteration bounds, but typically right now they require much stronger assumptions than some of the other methods. And if you're unrealizable, the current bounds depend on unknown quantities, meaning that we can't evaluate them. And if we can't evaluate them, that's problematic if we want to do things like model selection, because how can we select between different types of model classes? So that's the problem there, is that it doesn't give us necessarily a tool that we can use to select among what is the policies or policy classes we want to consider. And then there's some interesting new work in like primal dual approaches, but some of them have similar dependencies on realizability. So as you can see, this is sort of a very active area, and I expect there to continue to be a lot of interest in this area in the next few years. So what can we do? Well, we could just change the problem. So it's really hard to do this first thing. What if we do something easier, which is this problem before was to say, I have all these different policies, I want to do really well, and I want to get error bounds on the resulting performance. I'm going to switch the goalpost, and I'm going to say, what if we just have a policy class, say linear threshold policies, and I just want to be able to get the best policy in that policy class. And what I want to get bounds on is, compared to knowing the best policy in that policy class, how good is the policy I'm going to select in that class, and can I guarantee that sort of my regret is decreasing as a function of the size of that policy class and the amount of data I have. This is an easier problem, but I think it's still a really important one. And this is one that we know how to solve for at least certain classes of policies. So this is a recent result that we have with Xinquan Ni and Stefan Wager, who are both, Xinquan is a computer science student at Stanford, and Stefan is a professor in the business school and a terrific statistician. And so we've answered this for a particular set of policy classes. The idea is that we're thinking it doesn't just have to be linear, but we're going to think about particular when to treat policies. The idea being something like you don't make any decisions until one time point, and then you make a particular one of A decisions. So I'm going to not treat someone for HIV until their CD4 count drops below a particular parameter, and then I'm going to select which treatment regime I give them. So maybe I have 5 different treatment regimes, and I'm going to hit one of those 5. So this is a linear threshold policy because I'm conditioning on the CD4 count to decide when to start treating, and then I also need to decide what to treat. And similarly here, you could have something which is maybe a joint function of something like time and a health metric, and you decide when to turn a treatment on and off. So we can consider not just linear threshold policies, but we're considering this sort of when to treat setting. And I will just very, very briefly say that the insight for this is to look at sort of this decomposition of how much better is it to treat now versus later. And one of the things that has been really exciting for me is that it is leveraging techniques from sort of semi-parametric statistics, which I think machine learning people are starting to think about more now, and the econometrics people are thinking about machine learning for these types of techniques. And I think it has this really interesting idea of nuisance parameters, which is we don't really care about the importance sampling weights. We don't really care about our parametric estimates. We're using those to try to select policies or to estimate treatment effect estimations. And so the really cool idea to me is that we might be able to get much worse estimators for like our importance sampling weights or for our approximate parametric models. Like you might be able to get fourth root rates and still get square root rates for your resulting estimator. So I think there's a lot to be done in this space, and I just want to highlight that at Colt this year, the best paper was by Dylan Foster that was thinking about similar ideas, sort of orthogonal machine learning type ideas. So I think that this is a really interesting area for sort of bridging between different mathematical techniques from other communities and then extending them for these cases. I'll just highlight here that I think these type of estimators can do much better than fitted Q iteration. As you might expect, fitted Q iteration, if it's not realizable, is going to asymptote in its performance, whereas these estimators can continue to improve. And I think in terms of people actually using machine learning for the types of problems that we'd love to have impact on, I think that thinking about interpretability and thinking about end case uses is really helpful. And so one of the other reasons why we started considering this is because we thought about, well, what would we present to physicians in a way that might be useful? And something like fitted Q iteration, we can use very complicated function approximators like deep neural networks, which if we're running a car or like training a sort of control system might be okay. But you can get up with these sort of weird policies, whereas you can see there are these sort of these blips in the middle where you're changing between, you know, for two states that look almost identical, you suddenly change your policy. And so you could imagine as a doctor, that might look quite weird. Be like, well, wait, like if it, you know, if this particular health metric, this is a simulated example, but, you know, slightly changes suddenly, I turn it on here, but else I turn it off. Like that seems brittle in terms of the representation, because we'll generally have an assumption of things being smooth. Whereas what we did in our work is we imposed that structure on the policy class. We said our policy class has to have sort of a linear threshold in this case. That's what we were searching over. And so we got things that look like this, which, you know, you can sort of see have like this smooth, very smooth aspect, except for then a particular discontinuity. And I think this sort of interpretability can be particularly important when we're not sure if we have the right data or the right reward metric, and then people can give us feedback about, well, wait, that seems crazy, or that seems reasonable, or, you know, are you incorporating all the right state features? So I just want to highlight, I think there's a huge amount of work to be done for structural risk minimization, and thinking about this general issue of counterfactual reinforcement learning, and also accounting for these other sorts of issues like confounding, or another issue is interaction effects, which are super interesting. So it doesn't come up in my application domains a lot, but for my colleagues that collaborate with Uber, it does. What this means is that my probability of treating someone doesn't affect somebody else. Probably in healthcare, that's mostly okay, but not if it's sort of like a virus outbreak. And if you're, say, trying an incentive mechanism on Uber drivers, then they often talk. And so you can't assume that sort of individual treatments are totally independent. So there's a lot of other really interesting sort of technical challenges that come up as we start to think about deploying these in the real world. And I think there's a huge amount of work to be done. That said, I'll skip this part and some of the other areas. I do just want to highlight, I think there's good reason for hope. So I sort of told you a lot of reasons why this is so incredibly hard. If we go back to this example, we were trying to learn a policy that increased student persistence. We did a method that was based on importance sampling using these 11,000 student data. And what we predicted is that we could find a policy that was 30% better in terms of persistence. And so we did an experiment with another 2,000 students. and it was 32% better. And so that was really exciting for two reasons. One is that we actually improve student persistence, which highlights why machine learning and reinforcement learning can really help us in cases to have much better policies. And the second is that these methods could accurately predict that future before we deploy it, which I think is really exciting in terms of having methods that are robust enough for us to deploy in cases we really care about. And so with that, I'll conclude. It's been great getting to be here. If any of you guys are interested in future postdoc opportunities, or if you guys are interested in coming to visit sometime and thinking about some of the mathematical questions, please don't hesitate to reach out. Thanks.